This is the final Cock video for Day 04 structures. I want to talk about trees. We have a whole course after this on data structures. We're going to get to see tons more data structures. People spend their whole lives studying data structures. People spend their whole lives just studying trees, which is the data structure we're going to look at. We're going to start by just looking at a very simple kind of tree called a binary tree. Here is its definition. I've called it BT to represent the fact that it's a binary tree. B for binary, T for tree. Okay, what's that on binary tree? Well, it's either empty or it's a node. What's a node? Well, a node has a left child, L, and that's another binary tree. It has a value, V, of type X, and it has a right child, R. So two children, L and R, that's where the binary part is, and then we're putting values at the nodes. Putting the value in the middle between L and R is meant to be suggestive here about how to draw these. The video I'm going to make after this, I'll be doing drawings of all of the data structures we've seen using sort of an abstract notation that happens to be tree-like. That is a great way of trying to think about data structures in general in your head in terms of how things relate to each other. So if you've studied plant biology, you hear the word node and you think like, okay, yeah, that's a tree plant thing, right? A node is where a leaf comes out, right? Something branches. Okay, I'm picking up what you're putting down, Prof. Greenberg. But like, what is he talking about? What do these have to do with trees? So the advice I want to give here is like, if you don't understand something, you need to play with it. You need to like look at what the thing is, and then using the rules of the environment you're in, try to see what some of the consequences are. What can we build with these constructors, empty and node? So let's get playing. Here's a bunch of check statements talking about different kinds of trees. These are all valid, and it's worth looking at it and trying to guess what type is it going to have for each of them. So I'll try to give pauses here so that we can guess for each. Okay, first one, check just empty. Empty is the empty tree. It's kind of like nil, huh? What happened when you just checked nil with an implicit argument? Oh, right. It's one of these like, I'm waiting, Cock couldn't figure it out. Okay, if we do add empty nat, what'll it be? BT nat. Okay. Now that we're going to start using node, and we'll get some context so Cock will be able to guess the type. Node empty true empty. That's a kind of binary tree. What is it? What's its type? That's a binary tree holding booleans. Oh, interesting. Just like lists, our binary trees are going to be homogeneous. Everything has to have the same type inside. Okay, what about node empty, 5 empty? Well, that's surely BT nat. Both of these, we'll check in with more terminology in a bit. Both of these are what are called leaves, right? They're a node with no children, right? Both children, L and R, are empty. Here's a node that's not a leaf. Node empty G, and then the right child is node empty C empty. What type will this have? That's a BT base. Okay, what about this one? This is big. In fact, it's so big, it's kind of hard to see what's going on. Node, and then here's the left child, and then here's the whole right child, and then this is the value at the top of the tree, also called a root. We'll talk about that in a moment. And then the left child is a leaf, node empty, 12 empty, and the right child is not a leaf. It's a tree where 5 is at that subtree's root, that part of that tree, and then it has a child which is also the leaf containing 5. And this is what type? BT nat. Okay, so like, what are these though? So like, what I have here is I'm going to do a bunch of examples where I'll give the Galena term we gave, and then I'm going to draw it as a graph. So a graph it's not in the sense of like line charts where you watch the Dow Jones do whatever the Dow Jones does. It's you have like nodes, which are like points in space. I'm reusing a name, vertices, points, and edges between them. And those edges represent sort of a data structure holding other things. This is the notation I'll draw up. Here I have it just available in Cock. Okay, so empty we'll just draw as empty. Empty nat we'll also just draw as empty. We're not going to write the types. Okay, so for some reason my rendering is giving these extra weird characters. Please ignore them. They're not supposed to be there. And I've tried for 20 minutes to turn them off, and I've given up. Okay, node empty true empty. If we render that as a graph, we'd say, well, we have a node, and its left child is empty, and its right child is empty, and its value in the middle is true. And if you turned this upside down, it would look like a tree, maybe, where like this would be the root, and then these are the branches coming up off of it. Okay, let's draw another one here. Node empty, 5 empty. Okay, that's the same drawing. We've just changed the value. What about this one where we have some nested trees? Oh, interesting. Working our ASCII art skills. So here now you can see that this is maybe starting to look like maybe the root structure of a tree kind of dangling down. Computer science draws its trees upside down. It's a hard fact. It's embarrassing and it's frankly too late to change. We're just digging in. All our trees are going to be upside down. So here, this is a rendition of a tree where G is at the root, right, the top bit, and then its right child has the leaf C. What about this more complex tree? Whew. Now, what I like about this graphical notation is that, like, look, it's made it pretty clear how this is sort of has a certain branching structure that's relevant. This is, however, extremely noisy, right? This is a lot of stuff. So one thing you can do is you can leave off the constructors, right? Well, instead of writing a node, we'll write just the value at the point up here. And instead of writing empty, we'll just write nothing. So then we could write a graph that looks something like this. And this is how I'll be drawing graphs. This is sort of the nice way to do it. Right, so notice that we write nothing for empty. And we can just see, oh, this is the tree structure that we have. 25 is at the root. 12 is the left child. 5 is the right child. And then 5 is also this leaf, which is a child of that 5. There's a bunch of relevant terminology. So here a node has 2 children, L and R. A node is a leaf when both of its children are empty. Other less common terminology, 12 is a sibling of 5 because they have the same parent. You may be familiar with this concept from, families and siblings, right? So all of these are sort of relevant terms. The root and nodes and empty and leaf and things like that, those are the critical terminology. There are other bits of terminology that we'll come across as we go, but these are the important ones. Okay. The last of your homework on this one is we want you to write a couple of different functions on B trees. B trees, excuse me. That's a real data structure, but not what we're talking about. On binary trees, BTs. Size should count the number of nodes. IsLeaf is a predicate. It'll return a bool and it'll say whether or not your tree is a leaf. That is to say, a node where both of its children are empty. And numLeaves will count the number of leaves in the tree. Okay, and then that'll be it. Those are the assignments for today. I'll have one more video coming out soon where I'll do all these drawings, and then that'll be that, and we'll move on, and I'll start working on the day 5 videos. Okay, see y'all soon.